Hello, everyone, and welcome. My name is Eric Franzen, president of SemanticWeb.com. We would like to thank you all for joining us today for this webinar, a joint production between Dataversity and SemanticWeb.com, with our speaker, Rafael Richards of the Veterans Health Administration. Today, Rafael will be discussing transformations for integrating VA data with FHIR in RDF. We are also pleased to be joined by special guest, David Booth. Just a few quick points to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. However, we will be collecting questions. To ask a question, please type it into the Q&A module in the lower bottom right-hand corner of your screen, or if you'd like to tweet, we encourage you to share highlights or questions via Twitter using hashtag SemanticWeb. As always, we will send a follow-up email within 2 business days containing links to the slides, the recording of this session, and any additional information that might come up throughout the webinar. Now, to get us started on today's main content, please allow me to introduce David Booth, who has been one of the primary organizers of the Yosemite Project, to help put today's webinar into the larger context of that project. Hi, David.
Thank you, Eric. So the Yosemite Project articulates a roadmap for achieving semantic interoperability of structured healthcare information using RDF as a semantic foundation. Today's webinar by Rafael Richards describes some of the work that addresses Step 3 of the Yosemite Project roadmap. Step 3 is to define translation rules for instance data that is expressed in RDF representations. And Rafael's work demonstrates one approach based on spin rules to translate VA patient data from the VA's internal data models and vocabularies into an RDF model of FHIR, which is an emerging healthcare information interchange standard from HL7. So, Rafael, thank you for joining us today.
Thank you, David, and thank you for the introduction. It's a real pleasure to talk with you about what we're doing in VA to improve our capability to take care of patients inside and outside of VA. I will just bring up my slide here. See, David, could you bring up this deck?
So, Rafael, you just need to click on the tab that says Linked Vitals, and you should be good to go.
Okay. There we go. Very good. So I am going to talk briefly today about, I'm calling this Linked Vitals because this is a use case of the FHIR, HL7 FHIR standard restricted to the exchange of vital signs. And there's probably nothing more important to the patient safety and care than the fact that they have vital signs. So we are starting out with a very narrow use case of exchanging patient vital signs. Just to frame the question here in the big picture of what we are trying to do in the long term and in the big picture is a general problem statement of the capability to semantically integrate and exchange information between healthcare providers and their electronic systems for which we take primary use as our tool to take care of patients. In this case, we are using vital signs as our exchange medium, as our exchange data. And specifically, what we are going to do in this presentation to demonstrate the effectiveness of using RDF and model transformations to exchange data is to take the use case of a now emerging popular standard in the HL7 community called HL7 FHIR standard with the VA VistA system. Now, there are a few barriers to this, and these include that they all use different syntax, they use different data models, then they use different vocabularies. And all of these in combination can be put together as something what one would call a language barrier to exchange. And in agreement with what the goals of the Yosemite Manifesto is in making the data more fluid and liquid and exchangeable, one step forward is to minimize this friction is to use a common exchange language. And this would provide a model-neutral expression language allowing these systems to more easily harmonize and semantically align without the syntactic barriers, while leaving them still to express their information models in their native models. So to the big picture here again, what I will be talking about in more detail, just to give the bottom line up front, is a summary of the translation approach, which is first to take these two data sources, in this case the FHIR data standard and a set of vitals from a synthetic patient set of vitals, and to do some syntactic translation initially to a model-neutral standard of RDF. And the same with VistA. And in this case, we'll be doing natively expressing data directly from VistA's native data model, which is called File Manager, or FileMan for short, directly out of its the database using a projection into RDF as well. Now, these both have different models, but that's fine in RDF. It's model flexible. And then we'd be applying semantic translations as the next stage. That will do semantic alignment of the models, and in conjunction using rule-based mapping to harmonize these models with a common terminology. So from the input being systems that have different syntax, different models, and different vocabularies, the output of this pipeline and using this translation approach will give us information that has a common syntax, a common model, a common vocabulary, and thus a common meaning. A little background about VistA itself. The abbreviation stands for the Veterans Information System and Technology Architecture. And this is the information system that runs all VA hospitals, clinics, and care centers throughout the United States, Hawaii, Alaska. It also is the foundation, the database and the architecture. This is the foundation of other federal healthcare system information systems, including the Department of Defense at 900 care sites, the Indian Health Service at 500 care sites, many other states as well, including New York has about 24 hospitals that are going live with VistA. It's the most familiar electronic record system in the United States, and more than 60% of all U.S. trained physicians have already used it as part of their training, either as a resident or an intern or as a physician. It also happens to be open source and thus has a very large, thriving community of developers outside the VA who've implemented this throughout the United States and many other countries, including India, Japan, Mexico, Brazil, and the Empire Kingdom of Jordan that are using VistA to take care of 6 million patients as the nationwide electronic healthcare system. This is just a map showing the deployments of VistA throughout the United States, more than 1,200 care sites where this is deployed. And this is just to emphasize the relevance of this as a mover and in supporting interoperability. Now, VistA itself dates back almost 35 years. And this is when computers were very low powered with about 1/1,000,000th of the memory and 1/1 billionth of the disk space that our computers today have. It was therefore built by originally as a very specific architecture that could enable very patient medical specific algorithms and care and data management. And therefore, now running on today's computers, it's an extremely powerful platform. A very important concept about this as a highly specialized database combined with a programming language called MUMPS, or M, developed at Mass General Hospital. And this is very similar to what we are going to be talking about today in the fact that it is an incredibly interlinked and interconnected database. It integrates 150 applications into one single database. And the only way to do that is to have a very sophisticated way to manage data and metadata. And this shows an actual live, a real VistA, the 150 applications in the periphery, and how they share patient data, with the patient file being the central file, all integrated with each other. And this you will see how this plays out later as I talk a little bit about the data model of such a highly integrated system. Now, VistA is a hybrid NoSQL database, but unlike many NoSQL data stores, VistA is schema-driven and not schema-less. And what this means is that this schema can be lifted out and reprojected in a new form. And with this exposed data model, we can re-express this in standard machine processable form. And one of these machine processable forms that we are looking at today is the application of projecting this to RDF. This image below simply shows the core architecture of the system, which is a sparse multidimensional key value store as the foundation. And this can be reprojected to object, to relational, to hierarchical, to object stores, to JSON stores. And in the case of the VA VistA, this is projected to a more hierarchical store. So this ends up being a hierarchical graph store. And this lends itself very well to projection to RDF. Just to underscore the importance of data integration within such a system is the database management system. Again, this is the file manager, and it shows that in the left figure, we see the data flow from all applications going through the file manager versus a standard package such as an oncology package, which has far fewer connections. And you see the red line show dependencies and inbound connections versus the green lines on the left showing outbound connections, meaning that all the applications are dependent on the FileMan data dictionaries and data model for their data. Again, a little bit of internals of how and why VistA is very amenable to projection to RDF is the full exposure of the internals of its data-driven, metadata-driven architecture, showing these hierarchical files. Now, I will show you a brief demonstration of this live, but as a result of this projection of that has been a work for several years within VA and with the DoD in reprojecting the system, is the result of this projection is that now we have a query interface to this RDF projection, what we're calling the FileMan query language, and that leverages the native hierarchical graph model of VistA. And this will provide us web-based query access in various web-friendly forms, including HTML for human consumption and JSON for web-friendly forms for web application programmers, as well as various serializations of RDF, including RDF XML and JSON LD, and JSON LD being the preferred serialization for RDF for web programmers. So VistA can be queried both in HTML or RDF. In the HTML form, this is the human-readable, human-processable form, and we see we have a SPARQL-like query language in the query interface here, allowing us to pull any data from the system with such a query. Likewise, this same SPARQL-like query interface provides an RDF output, giving us a full machine-readable form of VistA data. And I'll just give a very brief demonstration here of this, and I will pull up a view of what this is live. Can everyone see? I hope everyone can see this. This is a live VistA. This is running out in California somewhere. This is all demonstration data. There's nothing real about this. This is anonymized data. And I have a couple of canned queries here just to show what this looks like when we're talking to a live VistA. And we can pull up any patient data, and we can traverse this just like any web system as well in terms of accessing it like any RESTful application, any modern web application. So, and if I look at the first 100 vitals for patient number 9, I can get this out as HTML and send a query. And we see here's what vitals look like in a VistA. This is the natively stored vitals. And we can drill into the hierarchical structure simply by clicking on this. Similarly, I'll go and look at the JSON form and look at the vitals in this form. And finally, I'll go in and look at the RDF form. I prefer the JSON LD serialization. And we can see the output here. is now giving us the @context sign, which is contextualization of the RDF data in JSON. So this is much more web programmer friendly. So I'll go back to the presentation and we'll get, let's see. Okay. So this is a live VistA, and this allows us very ready access to data.
Rafael, sorry to interrupt you. You need to click over to the Linked Vitals tab. There we go. Perfect. Thank you.
Good. Great. Thank you very much. So this is how we access data for the purpose of this demonstration. This is live data, and I certainly welcome everyone to play with that web link. And just for viewers who are fairly new to RDF, just a reminder what RDF is. It's as compared to HTML, is that HTML you can think of as just a human-readable version of web data. It's designed for humans. It links documents. And you can think of it as the document web, versus RDF is designed for computers, designed to be machine processable, machine-to-machine communication, allows us to link data and semantically, and it's what we call linked data, and provide and give us what we call the semantic web. And again, for this is probably a very popular diagram of showing just how linked data is, but this represents more than 300 linked data sources with Wikipedia, transformed RDF called DBpedia in the middle, linked to hundreds of data sources comprising billions of data elements. And the power of this, when linked to patient data, will transform healthcare, I believe, in a relatively powerful way, because it means it will take out health data out of the silos behind EHRs and systems and allow patients to have mashups of their data with environmental and geospatial and government and medical publications and genomics data in a way that will allow us to truly have a good, truly contextualize the patient's care and take better care of them. It will really push the science of medicine along with the clinical care of patients in a very big way if we can make this work. So this is the expression of VistA Vitals and RDF. This is the direct export. Now I'm using a tool here by a vendor. It's called Top Quadrant. It makes things easier, although there's tools such as Protege that are equally useful and valid. This one made it a little bit easier, had a little bit more functionality. And this shows the 239 instances from the sample patient that was in a VistA. It pulled all the vitals. And this is what they look like in the top grade composer. And this is just a visual view of what one set of patient vitals look like in RDF form. And you see the graph form of the data and the RDFS labels, including the blood pressure label. And similarly, we'll do the similar process with FHIR. Now these were, again, this was synthetic data, but the principle would be the same if we took data from any other EHR vendor's output. It would look like this, and what we leveraged was the XML schema of the FHIR model. And now you can programmatically transform this, and we took a shortcut and I used another tool, again a top grade tool, and this had an automated transformation from the FHIR XML schema to RDF. And this is what that looks like in visual form. Now the next step here is to do the translation of these to a common model, a common neutral model that will allow us to align them, both the data, the models, and the terminology. In our case, I was using Spin, but one could use any other rules engines, Java or Python, SPARQL, Jena, or any other tools for as a rule engine. This is the Spin tooling stack. It's a Spin architecture. And instead of relying on textual representation for SPARQL expression, Spin provides an RDF schema for SPARQL. And as a result, SPARQL queries can be stored as RDF triples together with any RDF domain model. And that enables linkage of RDF resources with the associated SPARQL queries, as well as sharing and reuse of SPARQL queries as part of a semantic web model. And an RDF vocabulary for SPARQL would be the first layer of a SPIN framework. So using the SPARQL RDF syntax, SPIN defines a very lightweight collection of RDF properties, and domain modelers can attach inference rules, such as SPARQL construct queries or insert-delete requests, and constraint checks and unit tests, such as ask or construct queries, to an RDFS or OWL class definitions. And then SPIN inference rules can then be used to derive new RDF statements from existing RDF statements at the instances of those classes. So this was a preferred choice for this because it was W3C compliant, it's exchangeable, is in RDF, and sort of keeps more to the ethos of having exchangeable rules. But this is the foundation for the rules engine. And again, one can use any other rules engine, but it was just a matter of pragmatism for this particular use case. And again, just glancing, looking at the slide here, SPARQL is very expressive, and it can be combined with other SPARQL rules such as OWLs, RL, and so on. This is just showing the data mapping rules engine, and one can stack SPARQL with SPIN and SPIN map, which provides us a mapping tool on top of SPIN that lets us map model to model, and then we can store those rules and exchange them in what the Yosemite Manifesto plan is to have an exchangeable rules database in a wiki style that would allow us to exchange these rules, and that is why they would be very transparent and expressible in a common language. And something like SPIN and SPIN map lets us do that. So SPIN map, data mapping rules engine, this simplifies the mappings between the different models, and it creates executable transformations. And all of this is represented in an RDF and an exchangeable form. And this just shows, again, a view of what the tool we use, which is top right, to do this mapping, create this mapping rule. And we can also do field mapping, and that gives us nested structures, and we can see some of the construct directives here to create these rules. We can also use SPIN map rules for standard terminologies, and here we're using LOINC, but one can use SNOMED or any others. They can also be expressed as SCOSs in RDF and incorporated in any such mappings from model transformations and terminology alignment. So with all of these rules done and executed, what we have accomplished is expressed VistA as RDF, FHIR as RDF, aligned their models, aligned them with the standard terminology, and ran the SPIN and SPIN map rules engine, and it correctly blended these together in a neutral model with the same as expression. And what you see here in this image is the fact that originally VistA expresses its information in the above panel, VistA patient records, as a text entity that combines systolic and diastolic, whereas the FHIR model expresses it as discrete systolic separate from diastolic pressures. And these are syntactically different, but their models are different, and the terms used are different too. And SPIN map allowed us to accommodate all of these as an exchangeable rule. So in summary, what we have done is taken two different data sources that have different syntax, different models, and different vocabularies. We've first done syntactic alignment to RDF, which allows much more fluid in a model-neutral language. And then we can separately address the differences in the models and separately address the issues of different terminologies. But in the RDF space, it allows it means we can have a standard tooling and much easier integration without that, with the friction to the left of the neutral model taken care of. Then we use SPIN and SPIN map to incorporate rules-based mapping between the models, to apply additional logic to separate the diastolic and systolic syntactically, and then finally apply standard terminology such that we've got common syntax, model vocabulary, and ultimately common meaning. Now, this was done several months ago, and I've continued some work on this, and we'll provide, so this will, again, in summary, this is going to provide us a stepping stone in a direction that will allow us to support the Yosemite Manifesto, move our data out in a formally expressed way that could be more universally expressible with common tooling, and allow us, more importantly, to exchange information meaningfully, but also to mesh that with many, many sources of data and really leverage the context of many other sources as patients start generating more and more data, the Internet of Things, and many, many more data sources. That patient's data will have to be contextualized in the context of their environment much more, which this will support that. Now, in the works, this work started many months ago. I've been supported by this with Ralph Hodgson from Top Quadrant, and he has generously provided his time to help with this project. And what we have here is a demonstrator that we hope to have available to demonstrate in a few months. And this will just be an online demonstrator showing what I've just talked about today, showing a prototype of a web-based application to automate the pipeline of a VistA to FHIR transformation. But again, that could be any EHR that can express its data as RDF, and it could be any other source of FHIR data for other objects besides vitals. But this just shows the pipeline, an automated pathway, and this may be too small to read the text, but you see these tabs, about four or five tabs on the top bar that retrieve data, retrieve FHIR records, convert the FHIR to RDF, and run inferences to show the results. This shows, this actually reflects this use case where this was used, and it shows that of the 239 vital signs, if you add up these distinct entities here, the blood pressure, height, pain, pulse oximetry, and respiratory rate, temperature, that adds up to 239. It's just that they are not expressed in a human readable form that well in the native structures, but now when pulled out as RDF and certain rules applied, it can be much more easily expressed and standardized and viewed much more flexibly. And in this case, this is now summarized in a nice table. Similarly, this will be pulling in a FHIR record from any external source and processing it similarly to this neutral model, and finally giving us the semantic alignment of the vocabulary models to give us the final result of an aligned information and models. Just as a background on what linked data does for us, it allows us to have both standardization and innovation. It allows us to have both at the same time, and we need both because there are thousands of models in healthcare that are all currently competing, whereas where we have a model flexible expression language like RDF, it means that they can all coexist peacefully in the same information space, and over time, incrementally, be mapped and modeled in this space. I can think of it more of as a data lake where they're all in the same space, and this allows for decentralized a model flexible approach versus a centralized model rigid approach, which is our current approach, which is the standards approach of the Yosemite pathway, which is standardizing versus, which is a centralized standardized approach versus a decentralized approach where the thousands of models in the healthcare ecosystem can peacefully coexist and evolve, incorporate new information, new data models, new concepts continuously as they need to, as healthcare evolves, and these can run in parallel. And this is just a brief summary of some of our traditional approach to healthcare standards in a linked data approach, which gives us data-centric granularity, gives us strong semantics that is intrinsic to the data, a model-flexible architecture which maximizes expressivity, gives us the capability to have multiple models to peacefully coexist in the same information space, which is easier and lightweight to evolve these models, and rather than downloading and aggregating, we're linking and federating the data to pull this together and integrate it. and lets us have very many specialized individual models that fit the needs of the end users the best. And that is the conclusion of my talk, and I look forward to your questions.
Rafael, thank you so much. So reminder folks to please drop your questions into the Q&A module in the lower right. Rafael, to kick us off, a pretty straightforward question about tooling here. Someone is wondering who is the vendor that made VistA in the first place?
Well, it's a long story going back about 35 years. This was actually a group of VA employees programmers at the time, who worked with physicians, who created this. They called it the hard hats, and it was considered the Underground Railroad. It was built open source. It was built in an open source way, in a federated way, 35 years before we knew the term open source. Meanwhile, in Washington, D.C., they were spending lots of money in a centralized way trying to create a system. And eventually, the centralized system did not work, and the field developed software that used the MUMPS language was extremely successful and ended up being deployed and developed in the field. This was a U.S. taxpayer-funded project. This is open source. It can be requested from Freedom of Information Act, or if you go to the open source EHR agency, or FHIR.org, you can download and run this on your own home system. It'll take you about half an hour to install this with a vagrant install. But it's open source. Taxpayers paid for it. It's owned by the U.S. public, and I certainly encourage the U.S. public to take advantage of it.
All right. Can you talk about some of the pitfalls, challenges, downsides, maybe potential objections to moving to RDF to store all this data? For example, is there a performance hit that should be expected?
Well, there's conflicting things, and today we do need to have in a way, a kind of separation of concerns. One is very high transaction processing capability, and the other one is exchangeability, and we need both. So today we have very large RDF databases that we've now achieved the trillion triple challenge. They are not so optimized for transaction processing, however. They're more designed as data resources that one can query to mesh data together. However, as a halo system, as an adjunct, or as a sidecar database system, this would be ideal. So this would not replace any current EHR. It would complement it, and it would mean that the tooling would be there to take other databases, whether they be relational or in JSON store or on NoSQL, wouldn't matter. But this would be the exchange, just the exchange medium, but the transaction processing would remain as is in the current EHRs. So the goal here of Yosemite Manifesto is more as an exchange medium and not to replace the transaction processing capabilities that require a high degree of security and reliability that our current database technology does very well. This is really more complementary.
There's a follow-up question that is very similar, but I'll ask it in case there's anything specific and nuanced to this. How about performance on very large patient stores? Are those slower or faster than native databases?
Well, this would depend. Now, with the open source MUMPS platform, this would be a development project to make this work. It has this, very good triggers, and one could literally simultaneously have a production system running in tandem and in parallel with a complete mirror image of the entirety of an electronic health record system running as an RDF store in parallel. And that would be leveraging the database technology but of the vendor, but many have store procedures or triggers that allow them to make these kind of real-time mirrors of their production systems. So that would enable, effectively, a real-time analytics platform and a real-time mirroring of a semantically queryable and exchangeable version of the entirety of the patient's record. Now, the limits today are at about 1 trillion triples. And if you look at a typical patient file, or just for reference, there are in a VistA about 630 statements or triples that describe the native statements that describe what is healthcare in a VA system. And by today's standard, that's not very big. It's less than 1 million triples. It's relatively small. A typical patient file would be, roughly speaking, on the order of millions of triples, 5 or 10 million triples, and it's been calculated roughly, if you took away the, of a population of 8 million veterans, if you took away the unnecessary and redundant information, we'd be looking at representing most of what is in a VistA or VA under a few hundred million, under a few 100 billion triples, which is certainly within the realm of today's technology to store this. Again, this would not be for transactional data. This would be for exchange and research, population research, and that sort of stuff. But for actual patient care, you still would need to use your core EHR system.
We next have a couple questions here that are talking about other data sets. I'm going to try to munch them together a bit here. The first is, any thoughts on the task of aligning with Epic's MUMPS data? And the second one is, do you have any experience in relating to Epic, Cerner, Athena, or Meditech?
Okay, so certainly. So it's very interesting that about 50% of the hospitals in the United States are running on MUMPS databases. Epic has several hundred hospitals, large academic hospitals running on their MUMPS-based Epic, and their equivalent to FileMan would be Chronicles. It's their equivalent. And it would require them to go in and reproject that system. To be a question of whether they would be interested in doing that. And similarly, Meditech has got about 1,500 hospitals. I think Epic's around about 400 or 500 hospitals. Meditech is about 1,500 hospitals, and combine that with all the federal sector hospitals of VA, DoD, and any health service that are all MUMPS-based as well. We're looking at about 2,000 or 2,500 hospitals out of a total of 5,800 hospitals. So it's close to 50% are running on MUMPS-based databases, which are very powerful and very amenable to reproject. They are very good RDF stores. They would be very good RDF stores and would make a really excellent project for the community to write an RDF store. We do have a triple store running on VistA already, a proper one. We have collaborated with Cerner in the Harvard SMART project, which was an RDF-based vendor-agnostic way to represent patient data. And so we were sharing data with Cerner using that model, and they have done that work with Josh Mandel up at Harvard Medical School at Boston Children's Hospital. So we worked with Cerner in that regard. And the other aspect of, in terms of other vendors now, so you could ask the question again of what you're asking about, performance or ubiquity among EHR vendors, or the applicability of this to MUMPS.
The first question was about the specific task of aligning with the MUMPS data.
Yeah, so that depends on the overlay that you're running on top of MUMPS, because MUMPS is a multidimensional key value store that one can overlay object stores, document stores, key value stores, JSON stores, and many stores can be overlaid on top of this. It's extremely flexible. The VA has its own database management system overlaid on top of the multidimensional store. They call it File Manager. And it's more of a hierarchical document-oriented store combined with this sort of graph store that gives this some of its inherent integration capabilities. So the short answer is that it depends, and it would depend on what overlay one writes on top of the MUMPS store. And I would, if one writes a native triple store on top of that, then there would be zero impedance. If you had something like FileMan, where it's open source and you have a lot of eyes on it, and we have some very intelligent folks out in the open source community who have written RDF visors for and projections for FileMan that's publicly available. And I couldn't say much about any other proprietary systems though, because I wouldn't know what their projection method is or what their overlay on top of, particularly for the Meditech or Epic systems. I don't have details on what their projections look like.
Okay. Next question is about curation and workflow. Is there a human needed to translate data source XML schema to RDF OWL? For example, human to build, RDF properties, the edges. Do you need basic ontologies to model any data source first? Do you need a hub ontology if we have 2 or 3 systems that we want to link together?
Good question. So what this exercise revealed to us, there are a lot of intrinsic gaps in the VistA native data model. In fact, it did not have a good vital signs native model, but we could express the data as RDF, but what we expressed also were the deficiencies in the underlying model. And we did have to fill in to create a neutral model. We did have to fill in these properties and some of these OWL properties as well. And so yes, there is work involved in doing this. And I guess the trade-off would be the real benefit in taking that effort is that it really means that the job of mapping more becomes, instead of system to system, more becomes a task of modeling and letting a rules engine do the definitive map. But it lets users of this method to focus on modeling rather than writing one-off, maps. And as the systems change and evolve, and it's a forcing function also for enterprises to really look at master data management. It really forces EHRs, owners and operators to say, well, if we take a model-centric approach, a look at the system from a data-centric, model-centric approach, exposing all the data that's in the system with this approach, and we can do this with VistA. This really lends a powerful argument to use RDF as a master data management tool for master metadata management, because it's very machine processable. Other forms of metadata management aren't as friendly for machine processing and aren't as exchangeable. So again, the answer is it depends, because the exposure of the system to RDF will expose model deficiencies and gaps that would have to be filled in with modeling, with OWL, and so on.
Eric, this is David Booth. If I could add to that, it's a really interesting question, and it actually gets back to the motivation for why the Yosemite project has 2 tracks associated with it, both a standards track and a translations track. RDF itself doesn't require that you have a hub ontology, but it is very advantageous to have one if one is available. So RDF is kind of agnostic about that. And the idea of the standards track of the Yosemite project is that is to encourage effectively those hub ontologies, whereas the translations track is to acknowledge whatever reality we currently have at any given moment, and saying, okay, given our current situation, we still need to translate. We do not have sufficient hub ontologies all the way through here, so we are still going to have to translate some. So that's actually quite an interesting question, and thanks for bringing it up.
Yeah, that fits back into the Yosemite Manifesto's hub ontology approach to having exchangeable rules. That's why the approach I took with this project was use spin and spin map, but again, you could use other exchangeable rules and methods. In terms of a question from Darren about other vendors beginning to use RDF and FHIR, I would say that other vendors are looking hard at it, at FHIR, and I think it's a matter of getting enough momentum behind RDF that would be a big enabler to help FHIR. So one aspect that will facilitate that is the fact that HL7 now has is formally collaborating with W3C as RDF as an exchange language, as a semantic substrate to represent a lot of the HL7 models, and RDF as this common modeling substrate, which would be a great facilitator for a lot of the HL7 mission and initiatives to express those models in a way that they could be slightly more machine processable and exchangeable and fit into something like the Model Exchange Hub and Rule Exchange Hub that David was talking about. So I think it's a matter of time, but now that there's more formal agreement in organizations such as HL7 to embrace HL7 as a semantic substrate, I think we can start to see more action here, and there is already action in expressing aspects of the FHIR model in RDF, and if that will be a silent substrate that would be less visible, whereas the FHIR standard is above ground, very visible to the programmers who find it to be more easier to use with RESTful interfaces and JSON and other web programmer friendly aspects, including OAuth and security. So it's a implementer friendlier tooling, but I think it will also, with the RDF becoming a partner with HL7, also become friendlier to the modelers to support the implementers of FHIR. So it'll be some time before this moves on, but there will be movement there, and if there's movement for FHIR, I think RDF will be pulled along with that as an adjunct and to assist with that. And part of my demonstration today was to see how RDF could facilitate RDF. Next question we have here is from Bin Sun, and have we built RDF formats for DRG, ICD, and CPT codes? I'm not aware of that, but there's nothing that would prevent that except for licensing issues to make any of those things public. But these sorts of things can be expressed in RDF. Most models can. It's a very model flexible language, and or as simple knowledge organization systems or SCOs. Again, it's an RDF, a simple knowledge thesaurus based on RDF.
Rafael, I can give a little update on that. Actually, this is David Booth.
Sure.
So the newest, or next, maybe I should say the next version of ICD, ICD 11, is actually being developed using RDF underneath the hood. There was a specialized interface to Web Protege that was developed by Mark Muson's group at Stanford University, and called ICAT. And it was used by over 100 domain experts, medical domain experts, around the world to collaboratively develop ICD 11 using an RDF representation underneath, an RDF and OWL representation underneath. So the users of the ICAT interface did not have to be RDF or OWL experts, and that's the way we want to leave it. They were medical domain experts, but under the covers, RDF and OWL are being used to represent this definition of ICD 11. And Mark Muson's talk yesterday, in his talk yesterday, he explained that they are looking into doing the same thing for CPT codes as well. That's
right, David. Thank you for jogging my memory. That's absolutely correct. So, and Web Protege and Protege are open source and fairly usable public resources as well. But yes, so ICD was, I think that was so that transformed. That was the ICD 11 transformation to OWL RDF using Web Protege as a platform is, again, highly supportive of the mission goals of the Yosemite Manifesto in demonstrating clearly that when you crowdsource something like as complex as a big terminology update, that they managed to do this. I think it was nearly 300 worldwide, the worldwide best experts who are motivated, subspecialists in their domain of expertise of cardiology or neurosurgery or so on, could then edit this without being experts in OWL or RDF And they updated this in a span of only about a year and a half. Now, heretofore, every update in ICD-10 took 10 or 15 years to update, and they updated it in about a year and a half. Now there's lots of testing going on before they deploy it, but the core period of time that they were doing the major updates, and this was hundreds of thousands of updates, was only about a year and a half. So this is highly suggestive that if we can crowdsource the knowledge management of healthcare information, of their models, their transforms, and their rules, with such a tool as the Web Protege / ICAT, that this would really facilitate semantic interoperability. And when you think about it, semantic interoperability is a human endeavor. It is something that only humans can really do ultimately. It's a matter of concept expression, a human-to-human concept transmission through a machine process, a machine pathway, but it is inherently a human endeavor. So this is something that really suggests that this notion of having a rules portal and an exchange portal that is open and a wiki-like portal to crowdsource interoperability, it will be transformative, and it will really accelerate our capabilities to have higher fidelity, higher quality data that is exchanged with more meaning, and to keep up with the changes in healthcare. And I think all of those together are very powerful elements to change, and for healthcare to adopt some of the best practices that the open source software community is using in terms of using GitHub and wikis and all these modern tools that everyone takes for granted now in the software world, and to bring those back into healthcare.
And for anybody that missed the webinar about the Yosemite Project, that is one of the components that was described about the Yosemite Project.
What a great segue. Thank you, David Booth. And thank you, Rafael Richards. I'm afraid that we are winding up on our time here. There is one more question that is a housekeeping question, and I'm going to take that one. Will the slides be made available? Yes, absolutely. For those of you who are logged in today to the live webinar, the recorded version of this webinar will be posted at SemanticWeb.com within 2 business days, and alongside that recording, that will be video and audio. We will also post the slide deck. So please do watch your inboxes for an email telling you about that. Additionally, your email will include information about registering for Part 4 of this series, Achieving Clinical Knowledge Convergence and Interoperability with Claude Nanjo. So watch your inboxes carefully, mark your calendars. The next episode of the Yosemite Project will be on Friday, December 5th, and then followed by 2 other episodes the subsequent Fridays in December. Thank you all very much for attending today's webinar. Thank you so much to Rafael Richards of the Veterans Health Administration, and thanks to David Booth for joining us. We will look forward to seeing everyone next time on the Yosemite Project webinar series.